Today I will be presenting about the paper called InceptionXML, a lightweight framework with synchronized negative sampling for short text extreme classification. And it was first introduced in SIGIR 2023. And I will be following this order for my presentation. First, what extreme multi-label classification is, it is classifying instances into a set of most relevant labels from an extremely large set of all possible labels, and it can be shortened as XML. And tasks such as prediction of related searches on search engines, product-to-product recommendation, query to bid matching, and dynamic search ads can be reformulated as XML problems with short text inputs. But using short text input for extreme multi-label classification has additional challenges because short text input queries are sparse and contain very few words, and they contain a lot of noise and non-standard phrases, and a large fraction of the classes are tail labels. So these challenges make it hard to learn rich feature representations. And these are the two main motivations behind the proposed framework here. The first is the need for a lightweight architecture in short text XML, and the second is the drawbacks of the conventional CNNs in short text classification. We need a lightweight architecture for this problem because using large pre-trained language models is the default for most downstream language tasks. But firstly, it's overcompensating for short text queries, and especially if it's extreme multi-label task. And secondly, the real-world use cases of short text extreme classification requires fast inference time. And thirdly, extremely large numbers of labels in this task leads to memory bottlenecks. And also, we cannot simply use conventional CNNs for this type of task because we can use them, but they are not optimal because the intent in traditional CNNs is capturing the occurrences of n-grams for representation learning. But for short text, the word ordering is not proper for efficient n-gram capture, and also much smaller sequence length restricts the effectiveness of the convolution over the inputs. That's why they proposed the framework here. And the contributions of the paper can be summarized into four. And the first part is the InceptionXML, which is a lightweight CNN-based encoder, which is different from conventional CNN-based encoders because it goes over the embedding dimension instead of the word dimension. And they also make an embedding enhancement module for learning word order agnostic representation of the input because there's the lack of structure in short text. And third is the training pipeline called SyncXML, and it synchronizes the label shortlister and extreme classifier to also mitigate the drawbacks of the dynamic hard negative sampling. I will be explaining this term later in the presentation also. And lastly, they do a comprehensive comparison with predefined transformer architectures. If we look at the related work, for extreme classification, actually recent techniques use attention mechanism and pre-trained transformer models, and they show promising results. But for short text extreme classification and just overall also, they are computationally costly. And for short text extreme classification, actually, we can divide the work into two categories based on the availability of the label metadata. And the first case is the first case of works. They assume labels as just numeric identifiers, such as done in STEC, which is one of the compared models to the proposed framework. They take the labels as just numeric identifiers, and the second category is they take the labels as text, and some example models are Decaf, Galaxy, Eclair, and Siamese XML. But the problem here, even though the additional label metadata is useful, it is usually known for only a small subset of all labels. So in this paper, they also use the first approach and accept the labels as numeric identifiers. And negative sampling actually means the sorry. Negative sampling is the process of identifying and selecting the hard negatives from the training data, because the hard negatives are more informative for training than easy negatives, since model can classify the easy negatives correctly anyways. And the scale of the eczema problem makes this step imperative, so we have to include this. And a popular approach for eczema problems, and also used in dense retrieval task, is using ANNS graphs. And works that follow the deep XML pipeline, they shortlist negatives by training an encoder on label clusters and then use the graph to create a static shortlist of hard negatives. And some other works use an alternate dynamic negative mining approach, which enables end-to-end learning of label shortlister and extreme classifier. And in this framework also, they use a dynamic hard negative mining approach. And first, I want to explain the proposed encoder, which is called InceptionXML. The goal here is to learn a classifier which, for a novel test instance, predicts the top K labels towards better precision at K and propensity scored precision at K metrics. And for this goal, to make this goal happen, the main body of the encoder contains 3 modules: embedding enhancement module, embedding convolution layers, and an extreme linear classifier, which can be seen here, the 3 parts of the framework. And for embedding convolutions, when models generate word embeddings, they can successfully capture fine-grained regularities. And in such paradigm, where each individual in the embedding dimension captures a fine-grained regularity, using convolutions over word embeddings can capture these couple semantics by convolving over the embeddings in a stack setting. And here, what we mean by coupled semantics is that the meaningful information is spread across several dimensions and not confined to a single one. And compared to traditional convolution operations that focuses on local patterns, like the n-grams, embedding convolutions create larger and enriched activation maps for the same inputs, requiring lesser parameters by using smaller filters. But of course, pre-trained word embeddings are typically not trained to find complementary semantic information over all of the embedding dimensions. And that's why they process the stacked word embeddings first with an attention-based embedding enhancement module before applying the embedding convolutions. And the module that they define, I will explain here. In short text classification, the sequence of the words doesn't follow the syntax of regular written language, and actually presence of a word is more important than its position. So we want to make the word order agnostic, but we can use techniques like pooling techniques. But pooling often results in loss of information. And for short text, the information is already very scarce. And the alternative to this is what they propose here, called embedding enhancement module. The module contains two orthogonal attention layers, and first is applied to the word dimension, and second is applied to the embedding dimension. And lastly, there is a projection layer, which encodes the information for both word level and the semantic level. Here you can see the sequential attention formulation. And here, E of X is the stacked word embeddings for the text input X. And XSA here are the intermediate embeddings, and they are projected to a 32-dimensional space to obtain the final enhanced embeddings, which are X sub ENH. Here, this enhanced embeddings are independent of the word order, and they make the model more robust to the lack of structure in short text. And for the embedding convolution layers, the architecture is motivated by InceptionNet. And there are three parallel branches of one-dimensional convolutional layers with filter sizes 4, 8, and 16, each with stride of 4 along the embedding dimensions and P output channels. After applying these convolution layers, they concatenate the results row-wise. And then a final embedding convolution layer, V sub F, is applied with kernel size of 16 and stride 4. And the result from this is flattened to form the final feature representation, H sub F. This is the final feature representation from the framework until now. And then in the linear classifier, the first layer R transforms the feature map from the encoder with a skip connection. Next layer W has one versus all classifiers for each label, which projects the features to the label space. And the model is trained end-to-end using binary cross-entropy loss. And then this is the training pipeline that they propose to make the InceptionXML, the encoder, more effective. Because what was described until now, it can scale to datasets with hundreds of thousands of labels, but it needs to be scaled up to millions of labels without requiring so much hardware resources. And the proposed SyncXML training pipeline improves the existing hard negative mining for dataset with millions of labels, and it is dynamic also. For the hard negative mining of labels, XML methods use the graph that I mentioned, but with fixed representations of data points, and they don't explore the dynamic hard negative mining much, and the model ends up using stale embeddings to create the shortlist, which is not good. The dynamic hard negative mining in this paper makes predictions in two stages. First is shortlists top K label clusters, or we can call them meta labels using a meta classifier. And then in the second step, it employs one versus all classifiers to the labels included in the shortlisted clusters to get the final predicted labels and performs back propagation. For label clustering, they construct a hierarchical label tree. And specifically, they use balanced two-means clustering to recursively partition the label set until we have a mapping C from L labels to L prime label clusters. And here, Light XML framework actually uses dynamic hard negative mining as well, but there are some drawbacks of this framework that they fix in this paper. And the drawback is the performance of the encoder here has a bottleneck because of the meta classifier. If we look at the graph, can see that the meta classifier falls behind of the extreme classifier. Model tends to learn representations that benefit the extreme task at the expense of the meta task. And Here, the SYNCXML has modifications that makes the encoder to learn representations that benefit both tasks, and also warm start the meta classifier training while they do this in a synchronized manner. First, what they do to make the two tasks similar to each other, they make their architecture similar. They add a linear layer W sub M with a residual connection RM before the meta classifier. And also here, S is the short list of all labels in the top K label clusters predicted by the meta classifier. And C inverse here is the linear label mapping. And they increase the extremeness of the meta task by enlarging the fan out of label clusters, the number of distinct labels. They increase it to make the meta task more extreme to match the extreme task. And also they perform detaching. To warm start the meta classifier training, they detach the gradients from the extreme classifier to the encoder for the initial 25% of the training, meaning the extreme classifier's output don't influence the encoder's parameters. The gradients from the extreme classifier are reattached, meaning that now the extreme classifier can also influence the encoder's parameters during backpropagation. Here, the reason why they don't fully keep the training of the extreme classifier separately is because detaching enables the classifier to adapt to the changing encoder representations without affecting the training of the meta classifier. And the losses are separate for the two tasks, and the total loss is the sum of these. And for experiments, they use a word piece tokenizer learned on the training data. And they use 4 publicly available benchmark datasets, which can be seen in table 1. And they use the evaluation metrics precision at K and propensity variant of the precision at K metrics. And here PSP at K metric is more aimed to evaluate the performance on the tail labels. And if we look at the main results, if we see figure 1, we can see that SYNCXML finds a spot that shows a high precision at 1 score while keeping the training time shorter than other models. And we can say now that changing the pre-trained transformer encoder with the light CNN-based encoder with also improvements in the hard negative mining process leads to better prediction performance and also faster training with smaller flops. Here, the sizes of the circles mean the calculation cost of the models, basically. And it's quite small for a SYNCXML model. And here in table 2, it shows that InceptionXML outperforms the previous SOTA STEC for all but only one dataset metric combinations. And in many cases, a single InceptionXML model outperforms ensemble version of STEC. Here the stars show the ensemble version. And we can see here the InceptionXML without being an ensemble, it outperforms the Aztec 3, the ensemble version of Aztec. And also compared to XML CNN, there's at least 10% improvement. And this result shows the effectiveness of the proposed approach compared to the conventional convolutions on short text queries, because this model uses conventional CNNs. And also there are gains up to 20% compared to the transformer-based model APLC XLNet and RNN-based model Attention XML. Inception XML outperforms Light XML also. As we mentioned, it also uses dynamic hard negative mining, but Inception XML fixes the problems with Light XML, so it outperforms. And also there are some label tree-based algorithms, Bonsai, Parabel, and DisMec models. And label tree-based algorithms were used before they start using the pre-trained transformer models. And the proposed framework here outperforms these label tree-based algorithms as well. And for ablation study, they look at the importance of the place of the embedding dimensions. They randomly permute the embedding dimensions before start of training to show that the model is independent of the initial order of embedding dimensions. And they do this for 10 times. And there's only, we can see in figure 4, the box plot shows the variation. There's only a slight variation in performance, which shows that the order of embedding dimensions has little to no impact over the results of the model. And also they trained the SyncXML on the Amazon titles dataset, but they randomly permute the words in the test set and they evaluate the performance. And for 10 permutations, there were not big changes in the precision scores, which demonstrates the robustness of the encoder to lack of structure in the short text query settings. And also SyncXML improves upon the hard negative mining technique proposed in Light XML. Here in table 4, we can see that as the fan out increases, the effect of the detached training improves the results more prominently. This can be because as the fan out increases, the extremeness of the meta task increases as well, and representations learned by the encoder for the meta task, they help the extreme task more when the gradients are reattached during training. And also lastly, they check the importance of the self-attention layers, and the effect of the sequentially applied self-attention layers is really small. The difference is around 1%. And this proves that the representation learning for short text queries of the model is good, that even without the existence of the self-attention layers, model outperforms the ensemble model STEC3 here and the transformer model Light XML. And they do comparison with transformers. In table 6, these are lightweight BERT models. They use these instead of the original because lightweight BERT models have similar number of parameters with the Inception XML model. And we can make sure here that Inception XML outperforms the light BERT models as well. And in table 7, it can be seen that the overall Inception XML outperforms the Distilbert model, but Distilbert's better results for the wiki data, we can see here, Distilbert outperforms the Inception XML at some cases because pre-training of BERT models was also done on Wikipedia, so that could be the reason. And also here we see another model called Distilbert no position, which is the BERT model without the positional embeddings. They compare the Inception XML model to this to validate the lack of word order in short text queries. And proposed model outperforms this setting as well. And for the computational cost also, there's decrement in training time by scaling the pipeline in SyncXML compared to the unscaled Inception XML. And of course, models train much faster than the transformer-based approaches. But still, Aztec is training time is shorter for Aztec. And the two models, SyncXML and InceptionXML, are extremely lightweight in terms of the model structure compared to pre-trained transformer-based models also. And models require significantly less flops while outperforming the other models. And the inference time is much faster. Using transformer-based approaches result in much slower inference time compared to SyncXML. And to conclude, in this paper, they proposed a lightweight CNN-based encoder for short text extreme classification, also using a self-attention-based word order agnostic module. And they propose a training pipeline SyncXML that synchronizes the training of extreme and meta classifiers and improves the hard negative mining pipeline for the labels. And they achieve these all while being computationally inexpensive compared to other models during training, inference, and model size. And this was my presentation. Thank you for listening.
Okay, thank you. Regarding the proposed encoder,
Yes.
how is its embedding dimension defined?
Embedding. It was
In the
in the
embedding enhancement module, they
yes,
use the two orthogonal attention layers. One of the word dimension and the other one is the embedding dimension. So
yes.
what's the definition for the embedding dimension?
Actually, it was in the paper. I don't remember the exact number.
So I mean, what is different from the word dimension? I think is generated from the distributions of words, but why is it useful compared to uh, word dimension?
Because for the word embedding, we see the local characteristics, and the other one is more generalized.
So I mean, the how is it generalized to capture the semantics?
They stack the word dimensions and
Then what's the word embedding model is used for constructing word embedding dimensions in this paper? Word to bag or others?
Oh, they mentioned glove, so I'm
Glove?
guessing glove, but they didn't clearly mention this actually. But glove was in the paper.
I am very wondering that the embedding dimension is also capturing the word information, but word dimension is why necessary for being used as the additional attention layers, even if they are using the embedding dimension.
I understand the question, but
Okay.
I can't explain it right now. I think I can look into it more because when I was reading, I remember that I understood this part, but I can't explain it right now.
Okay, I see. As the second question,
Yes.
for the negative sampling,
Yes.
Similarly, how is each cluster? Do they label for each cluster, right? Using
Oh,
meta classifier?
yes. They first label the clusters.
Then how is each cluster defined?
Uh, mm,
A cluster is composed of a combination of classes.
yes. There's from what I understood, the clusters mean the more general classes, and then inside the clusters, the labels are more detailed. And
Then how do they conduct meta labels for the clusters? Do they do that by manually or using a rule?
no, actually here, um, they don't do it manually, but the datas have the labels already, but
Labels for meta labels. The data
I
set has the meta labels.
no, it doesn't have the meta labels.
Mhm.
And they just I think based on the distance, they cluster the labels, and they also mentioned that they use the labels like integers. Labels are not the represented as text here. So I don't know. The meta labels are not defined in the data sets initially.
오케이. 다른 질문 있어요? 한글로 질문해도 돼요. 베이지 학생은 여러분들 모두 알다시피 어쩌면 여러분들보다 한국말을 더 잘할 수도 있어요. 이렇게 어려운 한국말도 다 알아듣고 있잖아요. 지금.
아니요, 이거 어렵지 않은데.
음. 정원열 학생 이를 좀 잘 볼 필요가 없나요? 그쪽 지금 국립의료원 쪽 하는 데 있어서 메타 레이블을 어떻게 정의했느냐 이런 것 좀 보면 좋을 것 같기도 한데. 궁금한 거 없어요? 네, 없는 걸로 하고. 질문은 더 없어요? Okay, Beyza, thanks for your presentation.
Yes, I will look into the questions more and
Okay.
let you know later.
Mm-hmm.
Yes.
Okay.